So the next thing we want to talk about when it comes to proofreading and writing is logic. So this is something like you would really cover in like a critical thinking class or something like that. Um, but it's important to really understand how exactly logic works, and it's kind of a funny thing because it's like, well, this is something that a lot of people just kind of understand inherently, but or they think they do at least, but then you kind of get into trying to figure out, is an argument logical, which an argument, um in a mathematical sense, is a proof, and it can be kind of tricky to really decide whether the logic follows or not. And um it really comes down to, well, is are all of the statements you're making true, and do they imply the next statement? And it's good to have kind of a framework to work with that in, if it's tricky to kind of fall back on. So I want to go through some of what you would look at like in an introductory logic class or something, some of the like symbols and different things that they look at, just a little bit of it, not too much here, because I don't think you see a lot of it, especially the symbols and stuff. We don't see a lot of it in math, but there is some of it that we do see quite a bit. So specifically, the big thing I really want to look at is what we call logical operators. And if you've done any kind of coding, like in R, for example, or even in SAS or Python or whatever, this is kind of a key part of coding, right? Is having these logical operators, where you basically have this binary thing of true or false, and you look at different combinations that lead to a true statement, or different conditions that lead to a true statement, or whatever. So like in an if statement in R, for example, you have to give it some kind of logical operator that will evaluate to true or false. So let's say we have two statements, okay, P and Q. And this is how we would, mathematical proofs are typically written in like paragraph form. So you'd have a statement, you have another statement, right? So you can think of them this way. So the different logical operators we can typically have, first one's called conjunction. This is where you put the two statements together. In words, we would say and, right? So actually just what I have written up here, let me make this just P comma Q, just so we don't confuse these two. This would be P and Q. So this means that if P is true and Q is true, it would evaluate to true. If P is false and Q is true, it would evaluate to false, right? So in logic, you typically would write this like this. Okay, so this little symbol right here, it's kind of like a triangle without the bottom, or like the caret symbol, or whatever you want to think of it as. This is like the logic symbol for and. So you'll see this sometimes on like Wolfram Alpha, if you put different conditions on, like if you type in the double integrals over like a rectangle, like -1 is less than or equal to x less than or equal to 1, and -1 is less than or equal to y is less than or equal to 1, it'll sub in this little symbol between them. So that's what that means. We typically don't use this one too much. We use a similar symbol when we're talking about sets, right? If we have two sets A and B, then we use this symbol to mean A and B, right? Technically it's the intersection, but it really has the same functional purpose. So we often can use what's called a truth table to kind of evaluate these things. So this kind of gives us a nice little picture of the different combinations we could have and what they would evaluate to. So if P is true and Q is true, then P and Q would be true. And every other combination is going to give us false. Okay. So again, these truth tables, they're not really used a lot in math, but they are kind of a good idea to like fall back on, right? if we really are trying to evaluate if something is true. And this is, of course, helpful in programming, like I said, if we need to put conditions on statements for writing if statements, while loops or whatever. So similar to this would be the disjunction. This is what we would refer to as an OR statement. Okay, so P or Q. This uses the same symbol, but upside down. Okay. In set theory, we would say A or B, right? So if X is in A or X is in B, then X would be in A union B. So for a truth table here, it's definitely a little more lenient, right? Because if either of the statements are true, then it will evaluate to true, right? So true, false still evaluates to true. False, true still evaluates to true. False, false is the only one that evaluates to false, right? So again, as I've said, you can see these in programming languages. So, maybe good to, play around with it and try it in there. Okay, so I just pulled this up RStudio, right? You could just look at, true evaluates to true, false evaluates to false, true and true evaluates to true, true and false will evaluate to false, true or false evaluates to true, right? So you can do these kind of things in there. And if you want to do like a not true, you do the exclamation point. And you can make different combinations of these, like not true, and false, or not false, or whatever, right? So you could kind of play around in there and look at that to get a better sense of these things, since it just does it automatically for you. So speaking of not, that's called the negation of a statement. This is pretty important because we often work with the negation of a statement rather than the statement itself, because it typically is easier. We're going to look at this in what's called a proof by contradiction. Okay, so not P is the symbol for it is this line with a little edge coming off of it here, and it's read as not P. Again, I don't see this a lot in math, but it does pop up every once in a while, so it's good to know. Of course, the programming notation for this is, the exclamation point before the letter. The equivalent thing in sets there would be the complement, as we mentioned. So that's everything that's not in A. See, I think that's good there. So then the other one we want to look at is the implication. This is very important. I mean, I write \implies about 100 times every time I make a homework or whatever, right? Because you're typically saying this implies this implies this, etc. So the implication, or sometimes called the conditional, is if P, then Q. So an if-then statement, this is kind of like the heart of proofs. You're just constantly saying, well, this is actually usually what you are proving, right? Where you get some theorem that says, if this is true, then this is true. And then you got to prove that, right? Or the author has to prove that and you want to read it or whatever. And they'll start with P and then they'll work their way logically over to Q. So the idea of a proof is everything has to be true and everything has to imply the next thing, right? And that's how we know that the proof is sound. So we typically, you sometimes will see it written as an arrow. P implies Q. I think it's much more common in math to see a double arrow. Okay, P implies Q. If you, in LaTeX, which I wasn't mentioning, you would use this \implies, and this is what it produces. It produces this double arrow. So again, this is read as P implies Q. Okay, so P is your starting point. Your your statement, and then Q is your conclusion to whatever that starting point is. And one thing I did want to go back and mention with the disjunction, by the way, it's the default is the inclusive or, meaning that you can have both of them, hence why I wrote this in the first statement of the truth table. That's how R works, for example. But sometimes you might mean or to be the exclusive or, which means that only one of them can be true. Okay. So you might see that in mathematical statements like, if this is true, then either this or this is true, but not both. And typically that's how it'll be qualified, right? Is that you would say, but not both, or something to denote that you are using the exclusive or. But if it's not otherwise stated, we typically would default to the inclusive or. So the negation on the truth table, of course, is just going to be the opposite of whatever P is. The implication is a little bit tricky. It's only considered false if the P is true and Q is false. So the hypothesis, which is what we'd call P, would need to be true, and then Q would need to be false. So we'd say a true statement implying the false statement, that would evaluate to false. Okay, so it's a little bit weird. Really only comes up, like, it's much easier to recognize with words or statements. Really only becomes tricky when you're looking at like a truth table or something like that. So, but this last one, this is these what we call conditional statements. These are very important because these are what most theorems are made up of. So we're going to spend time looking at the differences and the different combinations we can make with the conditional statements as well. There's many different ways that it's often stated. So it might not always be written as if P then Q, for example. Oftentimes we'll state things in terms of necessary and sufficient conditions. So we'd say like P is sufficient for Q, meaning that if you want Q to show that Q is true, it's just all you need to do is show that P is true. For example, but I don't think it's common, but I think it's more common just to write it in the if-then form. Okay, so I just want to write down two more definitions that we have from these kind of this area of logic, and then we'll go to the next video where we'll start breaking down those conditional statements. So a tautology is important. So this is a compound statement. Which just means that you have like a P and a Q in there somewhere. A compound statement S that is true for all possible combinations of truth values of the component statements, so the individual statements making up the larger statement, component statements that are part of S. Okay. So no matter what, you're going to evaluate to true. So for example, you might have something like P or not P, right? That's always going to be true no matter what. So the idea is it's kind of a meaningless statement, right? It, it doesn't really matter what you say. This is always going to be true. So in the proof context, it's kind of like we want to avoid this because it's not really adding anything, right? It's just kind of saying something obvious. Okay. Now, contradiction, this one's very important because we often prove things by contradiction, which is rather than proving something directly, we assume it's not true and show that it leads to a contradiction. So it's important to understand what exactly we mean by that. So a compound statement that is false for all possible combinations of truth values of the component statements that are part of S. Okay, so the opposite of a tautology, basically, where this is something that will never evaluate to true. So maybe like P and P, and not P, right? So this would be a contradiction. Okay. So again, we often are looking to, when we're proving something, we're often looking to create a contradiction. Like in the proof of that the square root of 2 is irrational, which we'll go through in one of these videos. The idea is that you assume it's not true, you assume that it's rational, and you show that that leads to a contradiction. Okay, so this is like the logical meaning of what we mean for a contradiction. So let's just look at an example here, just like for practice here. What if we have this? Okay, what if we have P implies P or Q? Is this a tautology or a contradiction or what? Well, we can use our truth table, right, where we look at the different combinations of P and Q, and then we look at this statement here. Okay, and it's actually probably helpful to have another column here for this one right here, right? So remember, I said the implication, this is only going to evaluate to false if P is false and the conclusion is, if P is true and the conclusion is false. So if P is true, Q is true, that's going to make P or Q true. So this is definitely going to be true. If P is true and Q is false, that makes P or Q true, which is going to make this true, because your hypothesis is true and your conclusion is true. If P is false and Q is true, this is going to be true. So this conclusion is going to be true, right? We need P to be true and the conclusion to be false for this to be false. And then finally, you have the combination of them both being false. Okay. So this is going to be true here. So false implies false. So this is a tautology then, right? No matter what combination we have, it ends up being true.